Welcome. In this video we're going to introduce the complex trigonometric functions, and we'll do so going through an example. To start off with, here's a joke which you may or may not find funny. In a written exam in freshman calculus, a student solves the equation sine of x equals 2. He writes x equals the arc sine of 2 and gets an F. He comes to ask what was wrong, and his professor explains that arc sine of 2 does not exist and that the equation has no solutions. A few years later, the same student has an exam in complex analysis with the same professor. He is very glad to see at least one problem whose solution he knows: to solve the equation sine of z equals 2. And well, you know the rest of the story. Alright, so the humor lies in the fact that the sine behaves a little bit differently in the complex plane than it does in the real plane. Let's talk about why that is. You'll remember that the sine of a number was defined in your first trigonometry or calculus or geometry classes by drawing a unit circle, measuring off a distance around the circumference of that circle, and then looking at the x or y coordinates to determine the cosine of the sine of the angle that you're talking about. Now, in contrast, in complex analysis, we define the sine and the cosine functions in this way: as fractions involving the quantity e raised to I times a multiple of z, or minus z. Now, there's nothing about the unit circle involved here at all. Where did these actually come from? Well, if you take the expression for e to the iz, we remember how to expand that from when we first talked about complex exponentials. And if we were to expand that complex exponential and e to the minus iz as well, we'll have a couple of equations involving cosines and I times the sine of different quantities. And if we combine those two equations and solve for the sine and the cosine, we'll get exactly these fractions. Your textbook kind of goes through that process. Now, while we're at it, we'll mention the hyperbolic functions as well. These are defined in a very similar way to where you may have seen them defined in a calculus class or an engineering class if you've run into these before. We call them the hyperbolic sine and hyperbolic cosine because of these expressions. You'll notice the only difference here between the sine and the hyperbolic cosine is the presence or the absence of the i's. And so the link is more readily apparent here. Now, hyperbolic sine and hyperbolic cosine are abbreviated the same way they were before, and sometimes this is pronounced sinh of z and cosh of z. And we may run into these functions as we go along. All right, now in your text, after defining these functions, your text goes through a lot of identities and a lot of properties of these functions. You'll notice that a lot of the identities are identical to what they were before when you first ran into the normal sine and cosine functions. We define a few other functions: the tangent, the secant, the inverse, the cosecant, cotangent. These are all defined in the same way they were in your calculus class or your trigonometry class. The section also talks about periodicity of these functions. It turns out that they are periodic. Even the hyperbolic functions are periodic in the complex plane, something that doesn't happen in the real line. We talk about the modulus of the images, how big they can be. We talk about the zeros of these functions, and we talk about their derivatives and where the derivatives exist. We also talk a little bit about what effect these functions have on sets, such as lines, in the complex plane. Now, please read through the section and make a note of all of these properties. You should at least understand the basic ideas of how these things are figured out. You'll see that all of this information about these functions is derived by looking at the definitions and working with these, sort of interpreting the effect of the exponential function combined in this way. Well, to illustrate, we're going to look at solving an equation involving a trigonometric function. Now, your joke involved solving the equation sine of z equals 2, and this is actually not a bad exercise. You should try it. Example 2 in your text will show you exactly what to do as it goes through solving the equation sine of x equals 5. Now, we're going to solve a slightly different example, one that's not in your textbook, but that kind of illustrates some of the same properties. Our equation is sine of z equals cosine of z. We want to find all values of z that make that true. Now, as with the equation sine of z equals 2 or sine of x equals 5, or sine of z equals 5, you first want to break out your definitions of these trigonometric functions. So I'm going to rewrite sine of z and cosine of z in terms of their fraction definitions. And then I'm going to manipulate things in a lot of the same ways that I manipulate normal real algebraic expressions. I'd like to get rid of these fractions, so I'm going to multiply both sides by 2i. I have here a negative exponent. I'd like to get rid of it if I can. So in order to cancel out this quantity with a negative exponent, I'm going to multiply both the left and the right hand side by e to the iz. Now when I do that, e to the iz will combine with e to the iz to make e to the 2iz, but e to the iz, when multiplied onto the e to the minus iz, will cancel things out. It will just create 1. And the right hand side will be as displayed here. Now at this point, I've managed to get rid of 2 of my 4 z's in the equation, and I can sort of combine things by moving the e to the iz, 2iz on the right over to the left. And since we're solving for z, I'm going to go ahead and move the constant -1 over to the right hand side as well. Now the next step, it would seem, would be to pair off this 1 minus I, to trim that. So I'll do that by dividing through. And if I take 1 plus I over 1 minus I and simplify that, I'll come out with just the quantity I. So e to the 2iz is I. Now how do I solve for z itself? Well, I'd like to get rid of the e if I can. And what I would do in normal calculus is just take a logarithm of both sides. Now if I do that here, on the right hand side I can go ahead and figure out what that is, and on the left hand side as well, it will work out, using the definition of the logarithm, that the logarithm and e will cancel each other out as long as you include a multiple of 2 pi I. And we'll have to include this multiple on both the left and the right. However, on the left you have just a multiple of 2 pi I and another multiple of 2 pi I on the right. I can combine those, maybe subtract them over, and it will still be a multiple of 2 pi I. I can also divide through by 2i. Doing all of that, what I'll end up with is simply the equation z equals pi fourths plus m times pi, where m is any integer. M represents sort of the combination of L minus k. Alright, now this is the answer. This is the set of all z for which the sine equals the cosine. You'll notice that interestingly, this only happens for real numbers. There are no imaginary numbers or complex numbers for which this happens, non-real complex numbers. And it happens, again, at exactly the same place as the normal sine and cosine are equal, at pi fourths plus some multiple of pi. Alright, well with that example worked out, please take a look at the section. Make a note of any questions you have so you can ask them in class, and let me know if there's anything I can help with.